I went ahead and started. I'm going to have to make sure that the audio works here. So before we begin, let me go ahead and remind you that today we're continuing with data structures and algorithms. Let me go ahead and, yep, it works. Okay, I just wanted to make sure so that in case we have audio. Anyway, to continue with data structures, again, a lot of the data structures you'll see are tree-based. And so we'll continue with some tree-based data structures. And then by the end of the week, or maybe early next week, we'll get into non-tree-based data structures. And the first one we already looked at trees a little bit with a review. Heaps are a way of visualizing, a way to visualize heaps is through trees, but to actually implement those things, you usually use an array under the hood. But now what we're going to look at are balanced binary search trees. So the idea here is that regular binary search trees may become unbalanced. All right? So for that, again, let's take a look here. If I inserted, just in a regular old binary search tree now, if I inserted the values 10, 20, 30, 40, 50, all the way up to 100, what would it end up looking like? I insert 10, now if I'm going to insert 20, it would end up becoming the right child of 10. Now if I insert 30 into a regular old binary search tree here, then it starts to become skewed to the right. Right? Now there's nothing special about inserting these things in order if you did them out of order, right? 100, here, I'll finish this, down to 100. If you went 190, 80, etc., it would be skewed to the left. Now there are plenty of binary search trees where it will be skewed to the left, right, left, right, left, right, whatever. There are an exponential number of unbalanced binary search trees, okay? But this is the clearest one that is completely unbalanced. What is the depth here? If I've got n equals 10, this is the number of nodes. At worst, what could the depth be here? Depth, careful, remember what is the depth? So what is the depth of 30? It is the length of the unique path from the root down to the node. So 1, 2 for 30. And if I've got 10 nodes here, what would it end up being? 9, or in general, n minus 1, or simply just order n. In other words, we have nothing, it's no better than a regular old linked list, right? It can, and again, this is not the only configuration, this is just the easiest one to see. You could have a configuration that went left, right, left, right, left, right, whatever, but it was still of depth order n. And it could be slightly less skewed, and it's only order depth of n divided by 2. But that's still order n, okay? So what we want is a binary search tree that balances itself, right? We want a guarantee on the depth. Right? We want D to be order, ideally, the best that you can hope for is log n, because it's a binary search tree, or it's a binary tree. And even in a full binary tree like a heap, you still have a lower bound on the depth of it being logarithmic, okay? So how do we go about doing this? Well, let's take this simple example of when things are skewed with only 3 nodes here. So I'll start out, and it's going to be, say, 20, 30, and 10. So this is clearly skewed. Is it skewed to the left, or is it skewed to the right? Left, right? It's skewed to the left. So if something is, heavy on its left side and you want to rebalance it, what do? You pull it to the right side. So what I want you to do is imagine a hill here, and that this thing is a chain, right? And that I'm standing up here on top of the hill, and I'm pulling the chain down over to the other side of the hill, right? What does it end up looking like? When I pull 20 up to the top of the hill, 30 comes down onto the other side of the hill, and 10 remains higher but still on the other side of the hill. Now, is this balanced? And does it look more balanced at least than the other one? Yep. This is called a right rotation. Right? Why is it a right rotation? Because we're basically pulling it to the right. Right? Well, what would it look like for a left rotation? And by the way, before we continue, let's make sure that we are dealing with binary search trees. Take a look at the tree beforehand. Is it a binary search tree? Everything to the left is less than the key. Everything to the left is less than the key. Now, what about the resulting table right here, or the resulting the tree right here? It's balanced, yes, but is it a binary search tree? Everything to the left is less than 20. Everything to the right is greater than 20. So yes, by simply pulling it up over the hill, we've preserved the binary search tree property. Likewise, what would this one end up looking like? I would end up with a left rotation. This is it is skewed to the right. And so therefore, to counterbalance it and rebalance it, we need to do a left rotation. And it ends up being exactly as before, 10, 20, and 30. All right? These are just simple examples with only 3 nodes. We'll look at the generalization here in a moment. But also, what do I mean by skewed? Right? It's clear when you look at this one small example that it's skewed to the right. But we're going to need a way to codify that in a way that a data structure, an algorithm, a computer would be able to understand what it means to be skewed. Okay? All right, let's take a look at a couple more examples here, though. All right, so let's say 30, and then 10, and then 20. All right. So that looks kind of skewed, right? Because there is no right child of 30, and in the left subtree we've got 2 nodes. Right? So it looks skewed to the left, but is it like it's skewed to the left over here? It's skewed to the left a little bit differently. All right. So, by the way, is it a binary search tree? Everything to the left is less than 30. Everything to the right of 10 is greater than 10. So, yeah. So how would I go about fixing this? If I just tried to do a right rotation here, what would it look like? I would end up pulling 10, 30, and 20. Now, is that a binary search tree? Everything to the left is less than 10. Less than 10? Nope. 20 is not less than 10. Yeah, go ahead.
Would it be a heap at this point?
Technically, it would be a min heap, yeah. But the relation there is not going to be clear for larger examples. Right? Okay. I want to make sure that I preserve the binary search tree property. So I'm going to do a combination of rotations. First of all, I'm going to look at 10 here. It has no left child, but it does have a right child, right? So in that sense, it's skewed to the right. So if it's skewed to the right, let's go ahead and correct that first and do a left rotation. Right? So step A. What will that end up looking like? 30, 20, and 10. Ooh, is that still a binary search tree? Yep. It's still not balanced, but it looks like this, which we know how to deal with. So I do a left rotation, and then I do a right rotation, giving me, that's part B, 20, 30, and 10. Right. So this is called a left-right rotation. It's a combination of the two. Right? It's left about 10, and then it's right about 30. Right? Left about or around 10, right about or around 30, right? You're kind of using those as pivots, right? That's what you're grabbing onto, okay? What would it look like from the mirror image? What would it look like if it's skewed to the right and then to the left? Right? So 10, then 30, then 20. Right? So if I'm going to correct for this, how would I end up doing my rotations? I do a right rotation first, giving me something that looks like 10, 20, and then 30. That's part A. And then B, I would do what kind of rotation? A left rotation. This is known as a right-left rotation. And it results in a perfectly balanced binary search tree. Okay? So 4 different types of operations, 4 different types of rotations. There's actually only 2 core types, but the other 2 are combinations of the first 2. Okay? This works for 3-node trees. Yeah, go ahead.
So, what exactly is a right or a left rotation? Because, like, I thought I understood what it was when it was, like, the first 2, but now...
So here's the left rotation, right? Again, imagine yourself as a hill here, and you're pulling it over to the left. All right? This one is you're pulling this to the left, but you're pulling it down here. Right? You're not pulling it all to the left up here. You're pulling it looking at this subtree here. You're doing a left-right rotation about that tree. And then in the second part, you're doing a right rotation about this tree right here. You're taking this root element here, and that's where you're pulling it over.
So what you were doing was you're doing a left about 10, so you're moving 10 to the left,
Which pulls 10 down here, pulling 20 up here to become the new left child of 30.
Okay, so you're disconnecting 10.
Ultimately, yes, what you're going to do is you're going to disconnect. In fact, there's no real rotation when you actually implement these things. You won't be implementing them, it'll be implementing them in pseudocode, but it's just a bunch of reference shuffles, right? At the end of the day, what happens here? 20 becomes the new root, and so 20's left child becomes 10, 20's right child becomes 30, 10's parent becomes 20, 30's parent becomes 20, right? And then whatever relationship you might have had above 20, that has to be updated too, all right? And then there are some swingovers in the general form of this. But before we can get to that, we need to codify all this stuff, right? What does it mean to be skewed, okay? For that, what we're going to have to do is we're going to have to define a new concept. Or maybe it's not a new concept, but maybe you've seen it before. But the height of a node U, in a tree, in a binary search tree or a tree, whatever, denoted H sub U, is the length of the longest path to any descendant leaf. Right? So the height kind of sounds something like the depth, but remember that the depth is a measure with respect to the root, right? If I've got, what's the depth of a node? It's the length of the path, the unique path, the one and only path, from that node all the way back up to the root, right? But the height is with respect to leaves. Height is a measure with respect to leaves, right? And it's not just, and it is just any leaf, any descendant leaf, that is, okay? So for that idea, let me go ahead and bring in, well, I need to define a couple of edge cases here before we do that, but I'll go ahead and bring in this tree. Oops. There, and then we'll get to it in a second here, because we do need balance factor instead, right? So here are some special cases. The height of a leaf is ... 0. Right? Why? Because if you're a leaf and there's no children here at all, then what is the length of the minimum path to any of your descendant leaves? You're already there, 0. Right? The height of an empty tree is dot, dot, dot.
Zero.
Well, you got to be careful. Then how do you disambiguate it between a leaf and an empty tree?
True. Would it be -1 then?
-1, right? By convention. That just makes everything work out fine, right? The height of a tree itself is the height of its root node. Right? And that's not going to be immediately relevant to what we're going to do, but if you want the height of a tree, then it's going to be equal to the depth of the tree, because at that point you're looking at the entire tree. Right? And if it's of depth 5, then looking at the that's the maximum value of any depth of any node. And so if you look at it from the perspective of the root node, then that also becomes the height, okay, of a tree, not a particular node. The height allows us to define a balance, right? So the balance factor of a node, U, denoted as BF of U, right, is the height, just short for balance factor, height of its left subtree minus the height of its right subtree. Right? Left subtree, right subtree. Right? And that kind of gives you a balancing kind of factor, okay? And as we'll see here in a second, a balance factor of 0 indicates a well-balanced subtree. Right? A negative balance factor indicates dot, dot, dot. A positive balance factor indicates dot, dot, dot. Now we'll understand that once we take a look at an example here. Before, I have a balanced tree here already. Let me see if I have an unbalanced tree. Unbalanced. Otherwise, I'm going to have to make one. Here we go. I'll go ahead and get rid of this other one. Oops. Okay. All right. Apparently, once it's pasted, you can't change it. All right. Fine. Really? Okay. No, you can change it. There we go. I'll get rid of that one. All right, so let's go ahead and take a look at each one of these nodes and indicate its height and the balance factor at that node, okay? Let's start at the leaves first. 5 is the least value here, right? So what is its height? It's a leaf already, right? So its height is what? 0, okay? What about its balance factor? You take the height of its left subtree and the height of its right subtree, and you take the difference. So what's the height of its left subtree here? There's nothing there, so what did we say that the height of an empty tree is? -1. There's no node over here, so what's the height of a negative, or what's the height of an empty tree? -1. So if you take the difference between these two, what do you get? 0. And that makes sense, because this is a perfectly balanced node. If you just look at this one node and look at its entire subtree here, it's a seed, right? It's only one node tree. You can't get any more balanced than that by definition. Likewise, what about all of the rest of the 27, 41, and 57? These are all going to be zeros. Why? Because they're all leaves, okay? It only starts to get interesting when we look at inner nodes. Right? So let's look at 9. 9, what is its height? The length of the longest path to any of its descendant leaves. It only has one descendant leaf. So what is the length of this path right here? 1. Okay. Now, look at the height of its left subtree. We already computed that, right? What's its height? 0. All right? So 0. And then minus, again, it's the difference. And what about the height of its right subtree? -1. So 0 subtract minus 1 is going to be what? 1. Zero subtract minus 1 becomes 1. Right? Let's look at 15. Right? 15, what is its height? 1, 2. What is its balance factor? You look at the left subtree and its height is 1. You look at the right subtree and its height is negative 1. So 1 minus negative 1 gives me 2. There we go. And you start to see a pattern here. What about 20? It's going to be 3 and 3. All right, let's go all the way up to 25 here. Okay. So, it's, well, first of all, 25, what's its height? 1, 2, 3, 4, or 1, 2, 3, 4. There is a descendant leaf, 27, that's only 2 away, but that's not its height. The height is the maximum among all of its leaf nodes. So 1, 2, 3, 4, or 1, 2, 3, 4 to that way, etc., etc. All right? And thus the height of the tree, now we have established that it's 4 because that's the root of the tree. But look at the balance factor of 25. What is the height of the left subtree? 1, 2, 3. Okay. Minus, what is the height of the right subtree? Also 3. So from the perspective of this node, its balance factor is 0. It looks to be a balanced tree. Right? It's balanced at the root, but it's not balanced anywhere, elsewhere, I should say. Look at 20. That's unbalanced, right? Because it is skewed. Which way is it skewed, by the way? It's skewed to the left. And it has a positive balance factor. 15 is skewed to the left. 9 is skewed to the left. Do you see the pattern here? If you have a positive balance factor, that means it indicates the tree is unbalanced to the left. All right? So, by process of elimination here, a negative balance factor indicates the tree is unbalanced to the right. Let's continue taking a look at a couple of more examples here. What about, let's say, 31? Right. What is its height, first of all? 1, 2, 3. Okay. And what is its balance factor? The balance factor of the left subtree here is, or the height of the left subtree, excuse me, is 0, because it's a single node tree. So 0 minus, and then what's the height of the right subtree here? 1, 2. So 2, it is negative 2. And that makes sense because it is unbalanced to the right. Right? Okay. Do we want to see any more? Shout out your favorite node there. What about 50? Just look at the picture and tell me what the balance factor is. 0, because it's perfectly balanced. What about 75? It's unbalanced to the left, so should it be positive or negative? Unbalanced to the left should be positive. Remember, it's A minus B, right? So it should be positive, and it's going to be 1 minus negative 1. It's going to end up being 2. Remember, an empty tree is going to have a height negative 1 by convention. All right? So let's write that down maybe. 75, its height is 2. Its balance factor is 1 minus negative 1, giving me 2. Right? And that is positive. Okay? So how does this help? This gives us a measure of whether or not something is unbalanced. And if we have a measure of whether or not something is unbalanced, that tells us when we need to rebalance it. An AVL tree, and AVL, there's nothing to it, that's just the author's names. The original paper had 3 authors, and that's the first letter of their last names. Right? An AVL tree is a binary search tree such that the balance factor of all nodes is -1, 0, or +1. You will have trees where you cannot, a perfect tree, of course, would have a balance factor everywhere of 0. That means it's balanced at every single node. That's not possible unless you have a full tree. Right? And you're necessarily going to, like if only a 2-node tree, you're necessarily going to be skewed to the right, or you're necessarily going to be skewed to the left. You need that 3rd node to make it a full tree and make it full a perfectly balanced binary search tree. Okay. Due to the balanced nature of an AVL tree, we have a guarantee that the depth is going to be order log n. Now, I'm not going to go through that today. We might eventually go through that. But even then, the analysis is a little bit more involved. You can establish a lower bound, and then there's some constant there in log, and then an upper bound, and there's another constant log. But we don't have to go over that. But by achieving an order log n depth, that means search is going to be order log n. That means insertion is going to be order log n. Crossing my fingers there. And then deletion is also going to be order log n. You have to be careful though, because if you just start inserting things willy-nilly without actually re-rotating it each and every single time, then you'll end up with something that is unbalanced. So you have to keep track of all of the balance factors, and when a balance factor becomes greater than 2 or less than -2, that's when you need to do a rotation. Let's take a look at just 2 examples here. If I had 30, 20, and 10, how do I know that I need to do a rotation other than looking at the picture? What are the balance factors here? The balance factor on 10 is, of course, 0 because it is a leaf. What about the balance factor at 20? Is it unbalanced at 20? It's going to be 0 minus -1. So it's just 1. What about the balance factor at 30? The left subtree is going to have a height of 1 minus the right subtree is empty, so it's going to have a height of -1. That gives me what? 2. Right? And it's positive, so I know that it's unbalanced to the left. What would the skew to the right look like? It would have a balance factor of -2. It's just a mirror image. Let's look at another example though. 30, where it's unbalanced to the left initially. Oops. 10. But then it's unbalanced to the right. So again, what are my balance factors here? This is 0. The balance factor of 10 is -1 minus 0. So what's that going to be? -1. It's not unbalanced. But now what about 30? It's going to be 1 minus -1. Why? Because the right subtree doesn't exist. Right? It has a height of -1. So 1 minus -1 is going to be 2. Right? But the key difference here is this is unbalanced. It's unbalanced to the left because this is positive. So you look at the left subchild, and is it unbalanced? Well, no, it's not. It's 1. But that tells you that it is also skewed to the left, meaning that you need to now do a right rotation. How do you know that you need to do a left-right rotation on this one? Again, you know that you're unbalanced, and it's positive, so you know that you're unbalanced to the left. So look at the left child. Do I have the same story here? It's not unbalanced, but it is slightly unbalanced with a negative value, meaning that it's unbalanced to the right. And so that way you know that you need to do a left-right rotation. Simply by looking at the balance factor and then looking at the relevant child, you know which one you need to do. Right? Now the details will be worked out as part of your homework. Yeah, go ahead.
So do you rotate from the bottom up or?
You always rotate about the unbalanced node.
Oh,
Right. Yeah.
But in the top example, there are still two unbalanced nodes, but they're still rotated.
But this is tolerated because an AVL tree is okay for 0, 1, or -1. It's not okay for 2. It's not okay for +2. It's not okay for -2.
So that's the twos and anything above positive or negative one.
Right. I mean, this is you would never get this starting from an empty tree. You'll never get this because it's unbalanced all over the place. You would have been balancing it as you insert elements. So this is definitely not an AVL tree right here.
Right, but -1, you still have to balance that out. Though.
Nope. I mean, it ends up being balanced. Either it'll end up being more balanced, or it'll still be unbalanced by -1, but that's fine, because -1 is fine, 0 is fine, 1 is fine.
So technically all you'd have to do is do the right rotation around 30.
Yep, for this particular example,
Or
yes.
for the second one.
For this one, you need to do a left-right rotation, because it is unbalanced to the left, and then it's slightly unbalanced to the right.
So it's the difference in signs.
It's all the signs, exactly. Yeah.
Could you demonstrate how you would balance a tree if it had, the bottom one if it had a 0 as well? So 30, 10, 20.
Ooh, okay.
So left of 10.
So 30?
Yeah.
Then what? Left child?
10,
10?
left child 0, right child 20.
Okay.
Excuse me, right child of 10 is 20.
Good question here. What are the balance factors? 0, 0. Okay. And then what's the balance factor here? 0.
And 2.
And this one is going to be 1 minus -1 would be 2. How did you get here, though? If you started with an empty tree, how could you have gotten to this configuration? Either you initially had something that looked like this, in which case you would have rotated already.
Mhm.
And so you never would have gotten to this configuration. Or you would have gotten to a configuration that looks like this, in which case you would have rotated and never have gotten to a configuration that looks like this.
Oh, yeah.
By always ensuring that you are rebalancing on each insert and on each delete, you will not have situations like this. You could never get to a tree like this, period.
Oh, yeah.
I just did this one so that we can, suss out what it means for height and balance factor definitions.
Oh, yeah. That makes sense.
Is there some kind of like formula you would use for how many right or left rotations to use and where?
You would only use one. Because once you rebalance, if you've got this very large tree and you rebalance a subtree of it, right, then that balances the entire tree. Now, don't take my word for it. It would require an inductive proof, but it does happen.
So we would never get something like the example on the bottom left either?
No, you'd get something like this if you inserted 30, 10, 20.
So we would have at most like 2 rotations to do?
Well, this is technically one rotation. It's a left-right rotation. It's a combination of rotation, but it's still one rotation. It's one operation. You can't just do this part and be done with it. You have to do this. In this configuration, you have to do this part, and you have to do this part to rebalance.
But
Okay.
I'm assuming there's still some sort of like, either like algorithm or like, I don't know, some sort of equation that could help you determine which.
Yes, it's the signs. It's the signs and the values of the balance factors. If you have a balance factor of 2, you either need to do a right rotation or a left-right rotation. How do you know which one to do? You look at the left child. Is that positive or is that negative? Right? I'm giving you the only possibilities right here.
Okay.
Right? Now, the left rotation and the right-left rotation, of course, would be mirror images of this. Okay? All right. We do need to think about these in more general terms, though. And for that, here is a generalized left rotation. Now, you are unbalanced at R, and R here is just the root of the subtree. And then, since it's -2, you know that it's unbalanced to the right. Or since it's negative, you know that you're unbalanced to the right. We said that, right? Yeah, unbalanced to the right.
Yeah.
Then you look at the child. C here is just a stand-in name for its right child. And it's -1, so you know also that it's unbalanced to the left. That's where you just inserted this new thing over here. Right? This is a generalization because this could be an entire tree right here. This could be an entire tree, and this could be an entire tree. So how do you go about doing a left rotation about the root right here? Well, remember, and I'll annotate these things, everything over here is less than R, so therefore everything over here is less than R. Everything over here is greater than R and greater than R. Why? Because they are in the right subtree. But what else do you know? Everything over here is less than C, and everything over here is greater than C. Right? So in order to preserve all of these properties here, what you need to do is you need to take this tree and swing it over to become the new right child of R, as it is right here. So once again, everything in T2 is greater than R, but less than C. So we have preserved the binary search tree property. T2 has swung over to become a descendant tree of C, so that preserves everything is less than C. It is the right child of R, preserving everything is greater than R. Okay. And likewise, T3 up here remains the right child of C. So you don't need to muck with this thing at all. Right. The general left rotation is exactly the same thing, but that was general left, right?
Yeah.
Yeah. So general right rotation, there we go. And it's fun making these things, right? Somewhat. It is just the mirror image of it. That this T2 swings over to become the new left child of R, right? Okay. Now, even more complicated than that is going to be the general left-right and general right-left rotations. So let's look at the general left-right rotation. So this is a left rotation, then a right rotation. And again, you know this because it is 2, so it is unbalanced to the left. You look at the left child, it is -1, so you know that it's unbalanced to the right. So you need to do a left-right rotation. And here you have potential for 4 trees. Your insertion of a new element A could have ended up as a descendant in T2, or it could have ended up as a descendant of T3 here. Right? In either case, though, when you do the left rotation, right rotation, T1 is unchanged, T4 is unchanged. It's still the right child of R, and T1 is the left child of C. But what happens is these 2 inner trees right here. This is root, child, grandchild. That's why I used RCG, right? This is the grandchild of this root right here, okay? What happens is it rotates over and then rotates over, and so T2 becomes the new right child of C, and T3 becomes the new left child of R. Right? G ends up being promoted all the way up to the top here, okay? So you've got 2 things that swing over. Swinging, rotations, everything that I just talked about is all just a visualization. When you actually go to implement something like this, it's just a bunch of pointer or reference shuffling, right? That thing's left child becomes that thing's left child. That thing's old left child becomes the right child of that thing over there, right? And you just have to get it in the right order so that you're not losing any of those references. Okay? Question? Yeah, go ahead.
It's A or A, one or the other.
One or the other. You don't. You insert, rebalance if you need to. Insert, rebalance if you need to. Right. You don't do like 10 inserts and then, oh, okay, now I'll do a rebalance. Right? Yeah.
Will they always be connected whenever there's like a left, right rotation?
Well, if there's no tree here, then this would end up being null. And you can shuffle around null if you really want to simplify your code.
Well, I just mean that, like, will they always be connected like that? Like, it's nice that the three primary sort of pivots involved are all basically like direct descendants of each other.
These three will always be there, right? These three will always be there. It's whether or not you have a subtree here that you have to worry about that makes this generalization. If you don't have these three right here, then you don't rebalance, right? If you had a tree like this, if you inserted 20, 10, 30, 20, 10, 30, no rotations are needed at all because the order that you put them in doesn't unbalance anything, right? This is a perfectly balanced tree right here.
Yeah.
Okay?
So when you, I'm sorry, I'm sorry.
Yeah.
So when you move T2 to C before you rotate the left,
T2 to C.
before you
I mean, if you're talking about like how you would implement this, I would say use temporary variables everywhere, right?
temporary,
Well, I mean, if you want to come up with T2, assign G dot left child, right?
oh, yeah.
There's a temporary variable, T2. And then eventually, dot, 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 C dot right child equals T2. So, hint, when you actually go to write the pseudocode here, why not store off everything in temporary variables, right? And then you've got basically 8 lines of pseudocode. Okay? All right. Let's take a look at an example. If you want to, you can go to this website yourself, visualalgo.net. And it's got a lot more than just binary search trees, but let's go ahead and create a new empty tree and start from scratch here. Let's go ahead and insert. I'll show you that that insertion in the proper order would not result in any rotations at all. If I inserted 10, 20, 10, and then 30, right? Oops. $20, $10, $30. A little bit faster here. Right? Then no rotations. Right? Now let's go ahead and insert, I don't know, 15. Before I do, though, predict what's going to happen. Careful. What kind of rotation? None. Why? What's the balance factor of 15? 0 because it's a leaf. 0 because it's a leaf for 30. 10, it's only unbalanced to the right, but only slightly, so -1 minus 0, so it would be -1 here. Right? And what about 20? The height of its left subtree here is 1. The height of its right subtree is 0. 1 minus 0 is 1, and so it's perfectly balanced. It's not perfectly balanced, but it is balanced. It's balanced enough. I mean, try to shuffle things around in your mind. Forget about the numbers for a second. Is there any way that you could shuffle these things around to make it a smaller tree? No, pigeonhole principle. 1, 2, 3. You're already full in the first 2 levels. You have to put that 4th guy somewhere, right? So, regardless of the configuration, it's going to end up with no rotations here. But let me put something in that will end up with a rotation. I don't know, 17? Yeah, wow. Not 187, but 17. Where's that going to go, first of all? It's going to be the right child of 15. Pause. What is the balance factor of 10 now? -2. It's unbalanced to the right. So what kind of rotation is going to occur? A left rotation about 20, meaning that 15 becomes the new node there.
Why left around 20? Is that because 20 is even more unbalanced than 10 now?
No, there was nothing, sorry, did I say 20? There's no rebalancing about 20 at all.
Oh, okay.
Let's go backwards here.
So
It's about 10, sorry.
oh yeah.
Left rotation about 10. Correcting the rotation in lower in the tree, or higher in the tree because it's the height, whatever, will necessarily fix not impact the balance factors above it, right? Because all you're doing is making the tree at most shorter. You're never going to increase the height of a subtree. You're only going to decrease it by 1. Right? You saw that, right? The old tree rooted at 10 here. If you look at just 10, it has a height of 2. But by rotating it, you necessarily make its height now at 15, 1. It makes sense too, right? Because if you've got this tree here, you want to shove everything up as far as possible to make it as shallow as possible because you want the depth, the height to be logarithmic. Okay? One more example.
Would you need to rebalance 20 as well? Or
Nope, no, because
it's
you can't.
zero?
Pigeonhole principle, you're done. Right? You only rebalance at 2 or -2 and it fixes everything. Again, don't take my word for it. It is an inductive proof that you would have to go through. But that goes beyond this course. I would do something like that and say computer science 423 or something like that. Right. Let's insert maybe 17, 16, no, I'll insert 13 and then 12. Oh yeah, go ahead.
So do you go up and check each balance factor until you find a 2 or -2, or do you go all the way to the top and then go back?
You do, yeah. Technically, if you were to implement this fully, once you insert it, this balance factor 0. Come back up here. That balance factor changes. That balance factor changes. Balance factor changes until you get to a 2 or a 0. At which point you fix it, and then you're done. You're done changing the balance factors, and you only have to change local balance factors during that rotation.
So you would start at the root you just added.
Well, no. You'd start at the node that you just added,
But yeah.
and then you would work up until you find an unbalance. Right? And then you don't work any further. You do when you delete, but that's another story. So and probably, on Friday. So let's go ahead and insert 13 and 12. 13 is going to end up being where? Right child of 10. 12 is going to end up being, by the way, it's checking the balance factor. Oh, darn it. No. All right, fine. There, what kind of rotation is going to happen there? That was a left-right rotation? I don't remember. Went by.
Yeah, it's fast.
All right, let's go slower then. You can change the speed here. So this will end up being a right-left rotation. Right, left rotation. And now it's a perfectly balanced binary search tree. All right. And now I'm running out of things because I should have gone like 100, 200, 300, and then I would have had many more intermediate values to insert. So you can play around with this to understand rotations. Write your pseudocode and debug it by looking at this as an example. You can, of course, create a balanced example. There, like a very large balanced example to start working with if you want to. Yeah.
I'm still not sure I understand this just by like looking at it, if that makes sense. But like you said we have to do this for an assignment. Is that like the next assignment or is that like this week's assignment?
No, this week's assignment is just the 2 programming, right?
Yeah.
Okay, yeah, because
Then this week is 5. All right, so 6. No, but no. We're just in the same module now of data
okay.
structures.
I believe 6 doesn't have any programming in it. It's just
6 is probably just written, yeah. It's got pseudocode programming.
This is in 5, I'll be crying right
No, this is in 6. Due on 15th. October 15th. And then we can look at advancing things again if we need to, because I think that after the 15th is the break.
Yeah.
Okay. So of course we won't have class on that Monday.